What I'll be talking about is an application of that, a specific part of an application of that. And it's related to a book that I'm writing for Manning Publications. It's currently available in early release. It should be available in print in the next couple of months. And it goes end to end from a raw data set. The data set is a data set of streetcar delays in Toronto to a deployed deep learning model. So it's fairly thin, that is, it's not going to a great deal of depth, but it's covering the whole end-to-end process in the book. As Adam mentioned, I work for Intact Insurance. I'm speaking tonight as a private citizen, but I will just mention, Intact is a great place to work. I've been there for about a year. It's been fantastic. So if you're interested in hearing more about Intact, please get in touch with me. I'll share my LinkedIn link a little bit later. So what I'm going to be talking about is something that in the context of doing a deep learning, end-to-end deep learning model on structured data, one of the things that people stumble on, and it's a fairly basic aspect of Keras, which is sort of a gateway drug for deep learning, but it has an aspect that is a bit tricky and isn't all that well documented. So I'm just going to talk about this particular thing, and that is doing a training run with Keras has basically two problems with it. The first is, by default, it goes until the bitter end. That is, it will continue, the training run will continue for all the epochs that you specify. And the second is, the model you get at the end is exactly the model that you have at the end. So the illustration here shows a real example from the book where a training run, it was 20 epochs, reaches maximum accuracy around epoch 13 and then gets worse. And so with nothing else, just taking Keras out of the box, we end up at the end of the training run with a model that is worse than the one we had in the middle, and we've used up some additional machine resources doing that training run. So the good news is that Keras integrates callbacks as a way to solve both of these problems. I'm going to talk a little bit about the two callbacks that let you solve this, and then go quickly through the code that implements this. An early stopping callback lets you stop the training run, if it stops improving on the measurement that you're interested in. And you can set a patience parameter that will let you go for a few more epochs in case maybe that measurement will improve. You also have a model checkpoint callback, which lets you save the best model. So the code underneath illustrates both of these things. The first one shows creating an early stopping object. So there you specify what you want to monitor, that is loss or accuracy. The mode, which would be maximum for accuracy and minimum for loss. And a patience threshold to see how much further you want to keep running once the training run stops improving. Number two is the model checkpoint. So this is saving a model. So you specify what path you want to save it to. Again, you specify what you're monitoring, either loss or accuracy, and a mode, maximum or minimum. You compile these into a list, and then all you need to do is add that list as a parameter to your fit statement. And I'm going to show a little illustration here that's in the book that kind of tries to get across the point of the value of callbacks. And you can think of Keras as a pie-making machine. And each epoch is a pie. And what we want is the biggest pie. So you think of the biggest pie as the set of weights for the model to produce the highest accuracy, for example. And the problem is, by default, what happens is you get the pie that's at the end of the run. So in this case, no, it's not the biggest pie, but that's what happens with Keras out of the box. Now, with the callbacks, you can specify that you get the best pie. So for model checkpoint, it lets you save the best pie, the biggest pie. That is the set of weights that produces whichever parameter you want to, whichever dynamic you want to optimize for, either accuracy or loss. And it also lets you, with the stopping checkpoint, with stopping callback, lets you stop once the process stops improving. So once the assembly line stops producing bigger pies, that you can stop. So these two aspects together let you get the efficient use of the machine resources that you're spending doing a training run with Keras. and be assured that you're getting the optimal model for your training run. And here's an example, a comparison that I ran last night. So these two runs were exactly the same, specified 15 epochs. The first run is with no callbacks. So it got validation accuracy 0.7208, the runtime of 10 minutes, and it ran all the way through all the epochs. And I got the accuracy for the last run. For run number 2, it had model checkpoint and early stopping callbacks with patience equals 4. I got better accuracy, not hugely better accuracy, but better accuracy, shorter runtime because it ran for fewer epochs. So this is just illustrating the benefit and what the value you get from using callbacks with Keras. And again, the reason for talking about this is as you're talking about the overall end-to-end process of creating a deep learning model that is trained with tabular structured data and delivering that as a deployed deep learning model, this little piece about Keras is one of the things that people struggled with quite a bit. It may be because the documentation's a little bit missing. So making sure people can understand this and take advantage of Keras, particularly because it's something people use as beginners with deep learning, is really important. There's a link to the book site if you're interested in seeing the book, the Git repo for the code that accompanies the book, including the code example here. And if you want to find out more about Intact, you can connect with me on LinkedIn and a link to my Medium blogging site as well.
How long have you been working on the book there, Mark?
It's been about 18 months now.
Nice one. Yeah, good work. And is that something that when you kind of due to publish it, you said it's like an early release kind of thing at the moment?
Yeah, it's available on the Manning site for early release right now, and it should be published in print in the next couple of months.
You said this is your first book. Are you enjoying the process? What did your employer think?
So yeah, it's been a lot more work than I expected. It's been a great learning process. One thing is it really forces you to understand something in a great level of detail to be able to explain it. It's a lot of work for the code. So the code, when you go right from cleaning up a raw data set to deploying a trained deep learning model, there's just a lot of code there. So I think I underestimated how much code was involved and the testing process for that. But it's absolutely been worthwhile. I'm looking to do another one. So I guess that's the true test of whether it was worthwhile. Yeah. So I certainly encourage anybody who has something they want to share with the community to give it a try. It's a great experience.
So Ganesh said, is there any way to proceed training further after callback at saturation point?
So I think that the question is, if you've stopped a training run, is the way to restart it?
Sure, we can go with that.
Yeah. So no. So in my experience, and again for the relatively simple example in the book, each training run was a distinct experiment, and then if it was stopped at a particular point, then that was the model that was saved. So it wasn't the training run wasn't restarted. It was stopped at the point that the criteria was met for the callback.
Thank you. We've got a question from Kapal. Kapal has asked, what was the motivation behind trying to solve this problem?
So I think what I was looking for, one of the things that I found in terms of deep learning, and this is why I was very encouraged to see the presentations from Jesse and Matt, is so much about deep learning as well. We've got these pictures of cats and dogs. Let's distinguish them. Here's an audio file. Here's a raw text file. And I think there are many really interesting applications of deep learning to tabular structured data. So that's really that was the goal that I was trying to accomplish. And I'd done some work when I was at IBM on their proprietary data sets. I needed to find a data set that was public, and the streetcar network had this delay data set. The other thing is, I think it's really important for somebody who's involved in a machine learning project to have an expert on the subject area, on the business problem as part of the team. It just so happens I'm very interested in streetcars, and so that was just an overlap. Something I think is really cool. It's an interesting problem. So an open data set, not too big, not too small, something I'm interested in. So it was a natural fit, and it was really messy. It was just an absolute mess. So there was a lot of material in the book about how to clean up a real world data set for applying it to deep learning.
Akshay has asked, usually we get different accuracy at even the same number of epochs. I'm not sure if I pronounced that right.
Yep.
Have you worked on problems that try to find optimal models at the same number of epochs?
Yeah, so the short answer is no. But in the book, it kind of goes through saying for a reasonable number of epochs. So there are a number of experiments that are repeated in the book. The one with the largest number has about 50 epochs in it, which for this application is more than enough. So it just the other thing is it's a relatively small model, so it can be exercised on a modest hardware. Now, I do make the point in the book that if you're paying for the hardware, which you would if you're using something like Paperspace or Azure ML, then limiting the number of epochs you have to go through to get a decent training run actually saves you money. So that's part of the motivation of going into some detail about using Keras callbacks. Is it's not just good practice; it can actually save you money by not having to not have to go so many epochs to get to a particular result in terms of training.
Great, thanks for that. I definitely butchered the pronunciation of epochs, but corrected.
It's Australian. I'm sure it's
yeah. Let's play with my accent.
Australian usage. Yes.
Yep, that's it. It was like data or data. Data, either or. Yang has asked, can you briefly comment on scaling for Keras training at production scale in the industry? Which one do you see more often? Distributed training in parallel, separate model, grid searches, or optimal settings, or larger GPU Spark clusters to pile on more data?
So I guess in terms of what I've seen, it tends to be frankly more of a brute force approach to sort of say apply more the time that it takes. So you have a team of very valuable resources. The time it takes to finesse may not be worth it. So what I've seen in a lot of cases is applying more resources and just trying to brute force it through.